Let's start this conversation by learning about some of the projects you're working on these days.
I would like to introduce or speak about Variables. The goal of the project is providing unifying benchmarking methodology for evaluating different indoor localization algorithms, which are based on RF signals. And as you know, indoor localization is an important aspect of almost all future uh, indoor Internet of Things applications. But the problem at the moment is that despite having many solutions out there on the market, both commercially as well as research algorithms, there is not a unified methodology for comparing them. So the crucial goal of the project is to develop a methodology and also a software and a hardware platform that will allow comparison of different indoor localization algorithms.
Great. So you mentioned hardware and software platform. Could you tell us about some of the platforms that you built, some of the software that you've written?
Yes, so as I mentioned, the project has to provide a hardware and software basis to evaluate different indoor localization algorithms. In first level, that is the twist testbed at TU Berlin, where we have a dedicated wireless sensor network testbed with more than 200 nodes. Second set of hardware that is used for the system under test or for the examined indoor localization algorithms is of course just typical Wi-Fi access points, which we are operating in order to support scenarios where one is using a wireless LAN signal for the indoor localization. And this infrastructure, very importantly, in the project is replicated at two physical places. So one physical deployment is at the Technical University Berlin, and the other physical deployment is in Ghent, in the iMinds Institute, which allows us to actually do a comparison between the performance of indoor localization algorithms under very two different conditions in order to be able to find out what are the intrinsic properties of the protocol. In addition to that, the Variables project requires hardware that will actually allow the benchmarking or the evaluation of the system under test, of the things that we are testing. And if we are speaking about indoor localization algorithms, of course, one of the crucial metrics that we would like to evaluate is, let's say, the precision of the indoor localization algorithm and how this precision depends on various external influences. Now, to be able to assess a precision of indoor localization algorithm, one needs to compare two things. From one side, the the output of the system under test, so the location which is provided by the system that we're testing, and then compare that versus a perfect, ideal, or previously known information about where exactly the thing that is being localized currently is. By calculating the difference between the ideal location and the output out of the system under test, one can calculate different performance metrics about the performance, the precision of the algorithm. So a crucial new element that had to be introduced in the project is the ability to have a reference localization system that will allow us order of magnitude more precise information about the location, which will allow us to compare and evaluate the system under tests that we are testing. And
Great.
for that, we develop a robotic platform. Here I have a 3D print model of what we call the Twist bot, which is the robotic extension of Twist. And the combination of this hardware with some suitable software allows this robotic platform to navigate itself in an unstructured environment like an office space with fairly high precision, so sub-meter precision. And you can see here that there is a tray at the top, and one can put, for example, a mobile phone that needs to be localized. For example, if you are evaluating the newly launched Google Maps indoor localization, we can put a mobile phone on the mobility base, and then we can specify a set of predefined waypoints where we can set our mobility base. The mobility base will locate itself at these waypoints with high precision. and then we will compare the output from the system under test, from the mobile phone, from the Google Maps indoor localization, and the internal information from the mobility base where it is. By comparing these two values, we have the ability to calculate or to evaluate the precision of the examined indoor localization system.
You have a great hardware platform with which you can do experiments. So during your experiments, how are you collecting data?
Yes, so essentially in Avalos we differentiate two types of input data that needs to be collected. If we're evaluating a closed commercial indoor localization system and we treat it just as a black box, essentially the only information or the minimum information that one can extract from the system is its idea about where it currently is, plus some estimate of the accuracy of this information. So if you map that back to my example about using Google Map indoor localization, you typically get on your screen the point which represents the current estimate of your location, and then you get the error circle or ellipse around that, which is kind of the system's idea of the certainty that it has in this estimate. So that is the minimum amount of information that one needs to extract when we're dealing with black box system. Using this information and information from the mobility platform, it is enough to calculate some basic precision and other metrics about the system under test. Of course, if we are now speaking about gray systems or white systems or system under test in which we are private to the internal behavior, where we have much richer APIs to access more of the data, then we are collecting a lot of information depending on the type of the source or the physical process that is used for localization. And here we differentiate between 4 different types of systems under test. System under test that use RSSI multilateration, systems that use RF fingerprinting, systems that use angle of arrival, and systems that use time of arrival or time difference of arrival. For all of these, we have a set of fixed parameters that are sampled from the system under test and that are fed into a suitable database for post-processing that allows us not only to calculate the end metrics with regards to the precision, but also to be able to make some kind of conclusions or deductions about the performance of the internal algorithms and their sensitivity to different changes in the environment, whether it is just physical change of environment from one testbed to another testbed, or something that's much more interesting to us in Avalos, how does these algorithms change as a result of different external interferences.
How much data does a typical experiment generate, and how do you manage all that data?
Yeah, so you can imagine, if we go to this first scenario where we just sampled the current estimate and the accuracy estimate from the system under test, it's by any means a very manageable problem. So that can be handled without any dedicated or optimized infrastructure. But the other use case where at the same time we would like to collect raw information about the things that are, the phenomenon that is happening on the RF, on the wireless channel that is used for the indoor localization, plus the information about the interference context in which the experiment is happening, plus information about the artificial interference that is generated by us as experimenters. This requires very careful design of the collection of the data, its storage, and its processing. To this end, for each of the categories of types of systems that I mentioned previously, we have defined a specific message structure that captures one sample of the data from the system under test. To minimize the latencies in collecting this data and optimize its storage, we have decided to use Google protocol buffers as a self-describing binary message specification and also serialization format that allows us to efficiently first act the data and minimize the latencies in its internal distribution among the different parts of the system, like the database, that we use for storing the data and also for the post-processing engines that then tap to the information from the database and calculate all the necessary different metrics for evaluating and ranking the protocols.
Oh, that's very interesting because traditionally, I think we've built in-house systems in our universities and research labs. What is that transition like, and what is the discussion that really led to using these more commercial services?
But we have a long experience with running the twist testbed over more than 7, 8 years now about storing user experimental data, in that case just generic traces. And the solution until now that we used was very classical. We had a RAID system with sufficient capacity, and all the experiments and traces from twist have been saved in the file system as textual dump files. For the needs of the wireless project, we would have to move this one step further and allow something that will support or provide a solution or migrate to a solution that will allow us not only very efficient and low latency storage of the information, but easy and dynamic processing. Because the old procedure works like that. So one runs the experiment and stores the data. The data is stored into a trace file. And then only after the experiment is complete, one downloads the tracing information and then performs its post-processing. In situations when one deals with a lot of data, one does not have the luxury to actually wait until the end of the experiment to find out that something is wrong or that we are not extracting the right data or there is some quality problem with the data. One needs to be able to do that in parallel, to be able to store the data for permanent storage, but at the same time being able to do some kind of a processing and evaluation of the data as it's being streamed. And faced with these demands, we decided to see what existing solutions are out there that we can leverage in order to achieve that. And that's why we migrated, for example, from the classical table-based or relational database approach that we used in the past to using Google protocol buffers or using a binary blobs for storing the data, augmented by several different indexes for search and discovery, and storing all of that in a schemaless database, either MongoDB, which uses binary JSON as its serialization format, or using HBase that can allow direct storing of the Google protocol buffer information inside the database.
That's great. Okay. So, does that make it easier or harder to compute some kind of summary of the data, or when you need to draw graphs for your paper, compared to the traditional MySQL or file system-based storage that you were using, and I think many of us are using even today?
Well, it depends, of course, on what kind of calculations one can do. So one needs to do. So if it is something that can be done into a online method where every incoming row in the database can be used to update some kind of statistics, then probably one can achieve something also with the old relational-based systems. One of the crucial benefits of the new approach is the flexibility in the formats, the fact that one is not forced to always operate in a fixed table structure. So adding new attributes that are important for the calculation does not mean completely restructuring the schema of the database. And secondly, the fact that by using a common or well-defined serialization format, one can use external services for doing some of this processing. So outsourcing some of this processing instead of doing that on a local machine, but interacting with services like Amazon S3 and then running MapReduce on top of the information that is stored in Amazon S3 buckets. So this is helpful from flexibility point of view and also from interoperability point of view.
Oh, that's great. So, do you start to use different tools and data processing techniques as a result of this?
Essentially, for a long period of time, there has been a bit of a gap. So, we as researchers, of course, have our own preferences or experiences with different tools. For example, my favorite statistical or experiment data processing system is the R statistical system. So, for a long time, this classical, very useful, very powerful systems for processing and processing experimental data, generating statistics, generating plots, have not been updated to deal with the new possibilities that are offered by these cloud-based services. But lately, we have seen several incentives, several initiatives that try to augment the capabilities of the old classical systems with plugins that allow seamless interaction with external cloud-based services, which allows one to have kind of, have the best of both worlds. We can continue using or operating in the old environments where we are very proficient. At the same time, we're able to seamlessly interact with the computational and storage capabilities that are available in the cloud. For example, very recently, so one very popular storage and processing facility, public storage and processing facility out there is the Google BigQuery, where you know that you can upload terabytes of data and interactively perform SQL-like queries and processing on this data. This can be integrated with R using this plugin called BigRQuery, and allows you really to fetch and process the data in the cloud and integrate that with the classical R-based workflow that one has, and in that way, maximize the benefits from both sides.
Great. So, what programming language, editor, compiler, operating system does your group typically use, and what do you use?
Well, the majority of the researchers in the group have preference for Python in terms of a general purpose programming language, and almost all data munging on text files and then calculating statistics or whatever, the majority of the group performs using Python code, and for visualization using Matplotlib. I personally am in a different camp, as I mentioned, so my preferred tool for processing is the R engine and system. And inside R, I use the so-called ggplot2 library. This very nice book, from Hadley Wickham, that defines the so-called, or implements the so-called grammar of graphs, and allows very flexible system for processing the information and then visualizing this information, which I think is very, very important whenever one deals with big torrents of data.
So, any other productivity tips you would like to share with us in terms of storing data, processing data, anything else?
In any project, one of the things that I try to always do is before one can make any decisions or conclusions based on the experimental data, one also needs to be certain that the experimental data is valid. Which brings us to the problem.
We're talking about outliers, right?
Detecting outliers. And by looking at different statistical properties and so local distances and so on and so forth, we can detect points that are potentially outliers, and then try to see after that whether this is real outlier or is it something that seems like an outlier but it's a real important aspect of the system that is tested. Because the crucial problem or the biggest mistake that one can make is rejecting some of the data just because it looks like an outlier. And I always try to be very conservative in rejecting any data, because most of the time, even the strangest looking data has something to say to it. And that's why some of the things that I try to do is, whenever I'm faced with some data collection problem, I try to, before starting any deep evaluation, interactive visualization, trying to create a graph where every measurement that one has done is somehow translated to a point in a two-dimensional or three-dimensional space on a graph. And just putting every single data from the experiment on the screen at the same time, because regardless of what statistics says, the human brain is probably one of the best outlier detector. And also an experimenter allows one to immediately see whether the whole procedure has been well behaving, where there are some things that should require more deeper inspection. So one of my suggestions is whenever you collect data, try before starting and calculating, statistical properties, mean value, variance. First, please, plot the data, visualize the data in the simplest form possible, and only after ensuring yourself that the data is sane or there's nothing there that warrants closer inspection, only then one should go to using these very powerful tools of statistics and other processing in extracting the values. Because before we can trust the statistics, we need to know whether the data that we are feeding in is actually valid or not valid. And I had many cases or many situations where while a sensor node was not calibrated properly, we had some hardware problem that created a certain offset in some measurements. And when you put the data, all of the data on one single graph, you can immediately see when something is wrong like that, and then either compensate or remove this data from the experimental set before actually performing some of the statistical measurements.
That's a great tip. Basically, plot everything. And another
Yes.
thing that we learned from you today is just see what's out there in terms of commercial services for data storage and data analysis. Most likely, it's a lot better than what we can build in-house.
Yes, and as I said, with this now, with the modern plugins, allow you to continue working with some of the familiar tools, but still outsource some of the processing into these cloud-based services. Whether this is Elastic MapReduce from Amazon, whether it is in-house Hadoop implementation, whether it is Google BigQuery, all of these services allow incredible processing and storage power, but still it can be tapped and connected with the existing workflows, thus maintaining the productivity of the researcher.
Thank you for your time today. We learned a lot from your experience, and we hope to translate some of your experiences to make our work more productive. Thank you.
Thank you very much. It was a pleasure.